Hello everyone. Welcome to this presentation for NimConf 2021. My name is Peter Munch-Ellingsen. I'm a computer scientist from Norway. You can find me on IRC as pmonk, also on the Nim forums and on GitHub with the same nickname. You can also find me on my website, peterme.net, where I publish articles and stuff, a lot of it about Nim. So my talk this year for NimConf is titled Why I Wrote My Keyboard Firmware in Nim. So just a little bit of background. I've been programming for a long time, and I've been programming microcontrollers for quite a while, but I've been doing it in Arduino. So most of you are probably familiar with Arduino. It's a C++ based library or ecosystem for programming mostly AVR microcontrollers. I started with that when I was quite young. I remember getting my first Arduino when I was still living in my parents' basement. And more recently, I wrote a game for something called an Arduboy, which is what you can see behind me here. And it is a very interesting. It's like a credit card sized game handheld console. It has a small 1-bit display, an Arduino Leonardo, and a couple of buttons like the old sort of Game Boy layout. And it runs Arduino code, obviously, since it's an Arduino based thing. And I started, like, I've been using Nim for a while. I did the Arduboy thing, and I did that. I wanted to try out writing Nim code for Arduino, because as we will see during this talk, Nim is a really nice fit for microcontrollers. And I've talked about this in the past in previous talks as well. And what makes Nim so great on microcontrollers are, you have the type system, of course, it compiles to C, so you get really low overhead, but also the macro system, which gives us not only the ability to make more readable code, but also gives us the ability of abstracting stuff away at really zero cost, which is really cool and really a really powerful tool when we're working on such limited devices, such as these AVR chips. So for example, when programming for the Arduboy, you're really stuck in this, like, do I want to have another sprite, add some more code? Is really limited in the amount of program and sort of data you can put into your game. So it's a really interesting sort of way of programming that we don't typically do when we're programming for normal computers. And Nim has some really nice features that can help us with this. The name of my talk is inspired by an article. I think the article is titled "Why I Rewrote My Keyboard Firmware in Zig." And Zig, so he was writing it originally in Rust, and then he transitioned to Zig. And so he was not a computer scientist, and a lot of the stuff that he mentioned was stuff about how much easier it was to use, how much easier it was to sort of do things, and also a little bit about like abstracting away stuff where Rust's really strict type system would sort of get in the way of abstracting away things. And this is something I feel that Nim does really well. It has a really strict type system, but it lets you use that to your advantage instead of having it as a roadblock. I've also been streaming the progress of writing this firmware. So for some of you, this recording setup might be familiar. So it's a little bit small in the bottom corner here, but this is one half of the keyboard. It is a split keyboard with sort of a hand soldered hand soldered matrix. Each half has a I/O port expander that talks I squared C over normal sort of 4-pole audio connectors, and they connect to one microcontroller that controls sort of the whole keyboard. So everything is done over I squared C, and that might be interesting in the future. So some of you might be asking, why do I want to write my own keyboard firmware in the first place? Why not just use something like QMK, which is one of the biggest keyboard firmware, sort of like open source keyboard firmware projects out there? And part of the reason is that, so I did originally use QMK after I had first started this up, although without the port expander, just with a TNC microcontroller just soldered directly into the matrix. I flashed QMK on it, and QMK is a really big project. It's a massive project. Really, at least to me, confusing to look around. Like it was easy enough to set up one keyboard with one microcontroller, just getting key presses. But setting up this sort of like twin setup with 2 port expanders, and if I wanted to have some more complex macros, stuff like that, if I wanted to make the keyboard my own firmware wise, I think it would have been really hard to modify QMK easily. Like I would have to really get into QMK and teach myself how QMK worked in order to do something like that. It's also quite massive in program size. So as I mentioned, for the Arduboy, we are really limited on these devices in how much we can do, how much program code, how much data we can put on these chips. And QMK, as we will see later, is really quite a big program. QMK is not written in Arduino. It is written in sort of a custom C thing. So it's not Arduino's fault that it's big. It's just the way you end up programming in C and C++, just to make it any semblance of readable and configurable, really makes the size balloon quite quickly. And I've sort of been mentioning Arduino, but not really talked about it. So what is my problem with Arduino? Why wouldn't I just write this in Arduino? Again, it's a bit about sort of the ergonomics of it and how easy it is to do stuff in it. C++ isn't the most ergonomic language. It is object-oriented, which is fine. But that also sort of limits you to a certain pattern, and being limited to a certain pattern is not very nice when you're trying to optimize for size. So you quickly end up in this, like, do I want to do it the correct way, or do I want to optimize for size? And if I optimize for size, my project is going to be really messy and confusing for people used to doing it one way, stuff like that. So an Arduino is also pretty wasteful on resources. This is not something that I really thought about much when I started out using Arduino. I mean, I didn't have any sort of idea of what that would even mean, but Arduino, since it compiles to C++, I think in my mind I was just like, oh yeah, it's about as good as you can do. It's as small as you can get it. And I did for a while teach an IoT class at the university here. where we were using a microcontroller with MicroPython on it. And MicroPython is sort of easy to use-ish. It's more ergonomic, so it doesn't have the C++ ergonomic issues that I mentioned. It's a bit more easier to use, but it's really, really huge. So when looking at the spec sheet of the device that we were using, it was really a quite capable device. But running MicroPython, you just ran out of program memory super quick. I remember I think I added like a screen, like a small like one bit display, and a font, and a little bit more, like one sensor to have something to write out, and I was already at the limit of my output, or my program size. So, and I've always had this idea like, oh yeah, but just use Arduino. That is small, that is nice. But when I started looking, so I had been told that Arduino wasn't great for size, and when I started looking at implementing this keyboard firmware, I really realized how big and how bloated sort of the Arduino ecosystem is. And part of that is expensive abstractions. We will get into this when I start talking about Nim's zero cost abstractions. But the abstractions in Arduino really take up a lot of program space. They store a lot of objects into memory. They pass around a lot of data that doesn't really change during runtime. So there's a lot of extra data that isn't really used for anything, or it doesn't have to be there on runtime. But we'll get back to that later. It also has few safety features, and this is partially because we're trying to optimize for keyboard or for program size. So for example, back to the Arduboy example, it has sprites and stuff like that. And sprites are stored in program memory. Program memory is a bit special. You can think of it sort of as a file on the Arduino system. It's just stored along with the code instead of stored in memory, like data would usually be. And all of these sprites are it's just a pointer to some data in program memory. And a lot of things in Arduino and in the sort of low-level C ecosystem, they're just pointers. So if you pass the wrong pointer, or for example in the Arduboy code, you pass a pointer and you pass a width and a height of that sprite, and it draws that on screen. But if you mess up the width and the height, or if you change the sprite, you basically lose, like you don't have anything in the compiler saying like, ooh, this sprite isn't the right dimensions or anything like that. So this sort of juggling of pointers isn't really great. But on the other hand, Arduino has a huge ecosystem, a lot of supported chips, a lot of supported libraries, and a lot of these libraries are tested across chips and stuff like that. So this is why I've in my earlier attempts is doing Nim on microcontrollers, I've been wrapping the Arduino libraries. So when I wrote my Arduboy game, I wrapped the original Arduboy or Arduino and Arduboy libraries. But for this, I'm doing everything from scratch. So introducing Badger, which is my own custom keyboard firmware. It's 100% written in Nim. If you look at the GitHub repo for it, it's 99.5% Nim and 0.5% makefile or something like that. It's incredibly small, like really stupid small. is really easy to modify. Everything, like when you open the main code file, everything is sort of obvious. You can really easily see what's going on. If you want to change like a key press, it's really easy to see sort of where you need to do that, what's going on in the code. And the way it does this, both the small size and the obvious code, is because of these zero cost abstractions. So it uses lots and lots of small compile time changes and optimizations at zero cost during runtime. And I really hope this will be the start of something bigger. I've started wrapping other chips. Also, like sort of wrap the low level stuff in a way that should be easily reusable by others. And once Badger is in a more stable state, it is working. I'm running it on my keyboard at the moment. But when I've sort of polished it a little bit, I will split out the libraries for low level stuff into their own separate projects that will be hosted separately on GitHub, so that if you want to start programming a chip in Nim, you can download that and download libraries for what you need and not have to go like copying code out of this project. And I really hope that we can sort of band together and port this to both more chips and start bringing more and more sensors into this ecosystem, this Nim on microcontrollers ecosystem. So hopefully this is the start of something great. I've also sort of borrowed the old Nim mascot as the logo for the Badger project, simply because it's sort of phased out. It's not officially used anywhere. And I kind of like the guy. I don't want him to get forgotten. So I'm using him as an interim logo for the time being, or at least his head. So I say it's really, really small. And this is what I mean by really, really small. So way on the left side of this graph, so that way for you guys, is the Arduino Blink. This is like the hello world of microcontroller programming. Most of these microcontrollers have an LED on the controller itself. And the blink is basically just turn that LED on, wait a second, turn it off again, rinse and repeat. The Arduino Blink example on the Teensy 2.0 comes in at 2,500 bytes, or just a little less than 2,500 bytes, which is quite big to begin with. I think in Nim with like when I did that in Nim, I think I was down at like 200 bytes, something like that. Then if you want to do, so as I mentioned, this keyboard uses port expanders. And this is just an I2C device that has I/O ports, sort of external. And with an Arduino sketch that is connected to one of these port expanders, blinking an LED over the port expander brings the sketch up to almost 4,000 bytes. So 3,936 bytes just to blink an LED over a port expander. In comparison, Badger, the full firmware, is 3,750 bytes. That is 2 keyboard halves, both connected via these port expanders, with a full 5x7 matrix on each half, 2 layers of keyboard layout, so I can hit a key and it switches to a different sort of layer where all the keys are different, or some of the keys are different. Macro key, so I can hit a key and it performs a function in my code. So for example, hit a key and it types A 5 times. And all of that stuff at 3,750 bytes. So that is 200 bytes smaller than just blinking an LED with Arduino library for the entire full firmware. QMK, as I mentioned initially, the smallest, these numbers are pulled from an article that was also using the Teensy 2.0, so it should be a fair comparison, of minimizing the size of the QMK firmware. And he got it down to, like, by disabling all the features or setting a feature set that got him the minimal size, was 12,220 bytes. And then the default is something like 22,000 bytes. So that's another 9,120 bytes on top of the smallest one. And as you can see, it just dwarfs Badger, or Badger dwarfs QMK. It's just so massive. Then the next one is the actual size of the program memory on the Teensy 2.0. I'm not 100% sure, but I think there might also be a bootloader that takes up a little bit of that space. But it is kind of an odd number, so I think maybe that is without the bootloader. But anyway, we can see that QMK takes up about 2/3, maybe a little bit more, of the Teensy 2.0 available program space. And Badger, like, barely registers. And you might think, well, if I only want to use it as a keyboard, like, what does it matter? For one, you can add a lot of features. When your base size is this small and adding new features are comparatively small, you can have your keyboard do a lot of stuff. This is all over I2C, so I can connect I2C sensors of all kinds. I can connect a display, I can add a lot of devices, and they can all be controlled by the same microcontroller. Another thing is that when we make stuff this small, we're no longer locked to these big chips. So the Teensy 2.0 is really popular with keyboard firmware or DIY keyboard enthusiasts, partially because it has a lot of output pins. But I'm using port expanders, so I actually don't have, like, I only have the I2C pins used on the Teensy. So it's really overkill for my project. And I think the Teensy 2.0 is something like $25. So it's not a cheap chip. And I've seen people do split keyboards, so the same as what I have. The keyboard is split in half and the two halves are communicating, but each half had its own Teensy 2.0. So that means you're already at a $50 price range just for the microcontrollers, before the switches, which are typically the most expensive part. For comparison here, we have the ATNI85, which is it is the smallest chip that I have on hand, which costs about $1. And it has I2C, so it should be able to run Badger. And as we can see, it's like, I could fit Badger almost 2 times into this microcontroller. That little red bit with 1510, that is the bootloader for the ATNI85. If I finished the firmware, I could, strictly speaking, push, like, I could remove the bootloader, but that makes programming it, like reprogramming it, quite a bit harder. So with that bootloader, I can program it with a normal USB. But as we can see, the ATNI85, like, we can use that for our keyboard. That means we can bring the cost down from $25 down to $1 for the microcontroller for our keyboard, which could really open up sort of the possibility for more people to be able to make keyboards, or just to make stuff like this in general. So that is another really cool thing. I also mentioned that the code is obvious, and of course, this is a really subjective thing. But what I mean here is that everything is just code. There's no, like, config formats that you need to learn. the code doesn't have to parse a keyboard or a config file. Typically, in a project like QMK, I think they have somewhere in their make file that it reads the config file and then it produces C files that goes into the firmware. And I know there is a website where you can sort of configure your keyboard and have it output your configuration file for you. But with this, everything is just code. So you just type everything in, and the compiler will complain if you're doing something wrong. And all the configuration is sort of in line with your keyboard. And apart from the reusable libraries, Badger is only 112 lines of code long, and all the configuration for the layers for each half, all of that is within those 112 lines. So it's really like you could probably fit that on a 4K monitor, the entire sort of thing that a user would have to read in order to see what's going on. Yeah, as I said, config is just macros. It converts into code. If you do something wrong, you will have type errors. You will have stuff like that to sort of guide you and tell you like, this point in your configuration is wrong. And that is not something that I had to write. Sure, I had to write the macro that rewrites it into code, but I don't have to write sort of the configuration checker because the Nim compiler does that for me. And the macros allow us to do what's called a declarative style of programming. I can tell my firmware like, I want to do this, and the macros turn it into the code that does that thing for me. So an example of that is how I set up columns and rows of pins in my code. So columns is just an array of pins, and these are the pins, the name of the pins that are on the silk screen of the chip. This is one of my really strong peeves with the Arduino system, is that pins are numbered, and the pin numbers aren't anywhere on the chip. So you always need to have the reference chart up to see what pin is which number and stuff like that. With this, these are the names that are on the chip. So it's really easy. You pick up the chip, you see, there's B0. I write B0 in my code. And here you can see I just say columns.configure. I want to configure all the columns as inputs, and I want them to have the pull-up or pull-up mode sort of enabled. And what you see on the bottom here is what that ends up as. And this is the code you would have to write in C to do something similar to what those two lines in Nim does. So here you can see you have this cryptic DDRB and DDRD and DDRB, which is the direction, so input or output, and then port D and port B, which controls pull up or normal mode. And as you can see, the configure macro here is smart enough that all the B0, B1, and B2, those are grouped together. So it's one write to the DDRB and is one write to the port B, even though I configure 3 different pins on the same port. So it does smart things like this, and that not only brings the code size down. I actually tried this first without this, and this actually brings the code size down quite a bit. But it also means that when I'm using the port expander, I have a similar configure macro to this, and that cuts down on I2C communication, which makes the whole thing run faster, which means we can add more sensor because there's less overhead. And all of this, like this stuff, sort of bubbles up. So when the low level stuff is this efficient, the level above it isn't sort of building on overhead. So it's really the benefit sort of stacks. Another thing, this is the configuration for my layout. This is the default layer on the right hand half of the keyboard. I'm using the Dvorak layout, so ignore sort of where all the letters are. But as you can see here, I'm just typing the key. I want to have the 6 key, I type a 6. I want to have an N key, I type an N. And this is this is code in my firmware. There are a couple of weird things. For example, you can see the modifiers on the right hand, so shift and control, for example. They have this .m thing. And that is a thing to make the type system happy. So the type system won't allow me to mix keys and modifiers, because those are two separate things. They are both numbers, but they are separate things when sending them over USB to the computer. So the number ranges. So if you type mod control or key A, those might share the same number. So in C code, if I were to write this in C, that would mean that these would collide. Those would not be, or sort of, it wouldn't ensure that you're putting keys into where keys go and modifiers into where modifiers go. So you could try and send a modifier as a key, and in your code it says type shift A, but what happens on your computer is maybe it puts out AB because shift is a B. And this is sort of the type safety I was talking about earlier, and how you can't easily sort of mess up, and this gives you a lot more safety. You can also see the switch thing. That is just calling a function that I have defined that switches the layer. It's that easy to give a macro to a key. So yeah, I talked a bit about type safety and macro magic. The layout for the keyboard is stored in PROGMEM, and this is going to get a bit technical. But as I said, the program memory is sort of where we can store stuff that isn't going into RAM on the microcontroller. And this program has to be read by special PGM read X, where X is sort of the size we want to read. So in the case of a key, which is uint8, that is PGM read byte. In C, this pointer to this to our mapping would just be a normal pointer. There would be it would be a pointer to a character. There would be no mechanism in place telling us that we couldn't just read that. That we would have to use this special PGM read X thing. In Nim, PROGMEM is a special. I've made PROGMEM a special type, which means that I can't just pass it to anywhere. I have to read it out using the PGM read things. But if I store an array of PROGMEM stuff, I have also overloaded the array access function, which then automatically calls PGM read X, which means that turning stuff into PROGMEM is just like a drop-in replacement. You just change it in your definition, and all of a sudden it uses a different read function, and all of that happens automatically for you. So the code is super readable still, but now you're storing it in a different part of memory, and it's all type safe, so you can't mix and match by accident. As I mentioned, also keys and modifiers are distinct, so we can't mix keys and modifiers. There are other similar mechanisms in place that means we can't mix and match stuff by accident. Pins are also compile time objects. In Arduino, a pin is an object on runtime. In Badger, pins are compile time objects. So I store the port and the number, but they are compile time objects. So when I want to use them, they get rewritten into those port and DDR statements you saw earlier, and also read statements. And that really cuts down on size. It really means that we don't have to keep objects for a pin definition during runtime. The only downside of this is that pins are, since they are static, it's slightly less dynamic what you can do with them without being clever. But this really doesn't come into play as much because a pin is more or less a static thing. I don't think I've ever seen a project where you can, on runtime, switch a sensor from one pin to a different pin, or like change a pin to do something else because it's physically soldered to something. So this isn't really a big issue. Pin extender is also distinct from the internal pins, but it's the same interface. So using the pin extender is just dropping in a couple of lines to like enable it, turn it on, tell it which I2C address it has, and then you can do the same, like pin extender, like P0 is pin extender pin 0. And we can use that in exactly the same way as we would use internal pins. As I mentioned, this compile time rewriting really cuts down on program size and also speeds up our program. And one really fun thing I noticed was that I was having some weird issues, and it turned out that it was too fast. So I configured the pin and I tried to read from it, and it didn't have enough time for the voltage to stabilize in the matrix. So I got bogus readings. And this is something you would never have run into with Arduino because you have too much overhead. But since all of the overhead was gone, I had to add a 1 tick delay. So that is sleeping for 1/80 millionth of a second, or whatever 80 megahertz clock speed gets you for 1 tick, just to fix this issue, to let the voltage in the matrix stabilize. So that is how low overhead this system has. But yeah, that was all from me for this time. I hope you've enjoyed the talk, and I hope I've piqued your interest for programming Nim on microcontrollers. Hopefully this will go to great heights, and I hope to see you all coding your microcontrollers in Nim in the future.